Hello everyone, my name is Jia Arora and my student ID is 2510999107. So today we are diving into something that quietly powers a huge chunks of your internet experience and most people have never heard of it. It's called QUIC and it's basically a next generation protocol that's redefining how data travels across the internet. The big idea, we are overcoming what's called TCP tax, the hidden cost of using old, outdated technology in the world that's now mobile first. So let's break it all down starting from the basics. So let's come to the slide 2. So what exactly is QUIC? QUIC is a modern transport protocol. Think of a transport protocol as the set of rules that decides how your data gets from point A to point B over the internet. It was officially standardized as RFC 9000, which is basically its official rulebook published by the Internet Standard Body. Here's what makes QUIC special. The three things. First, the foundation. QIC is built from scratch on top of something called UDP, a lightweight delivering system. Unlike older protocols, QIC is multiplex, meaning it can handle multiple conversations at once and it's secure by default. Second, the integration. Traditionally, internet connections have two separate steps, one for transport and one for the security. QIC merged both in one using TLS 1.3 for encryption, creating a single unified end-to-end connection. And third, the goal. QIC exists to radically reduce latency, that's the delay you feel when loading a page or starting a video call, and to permanently fix the structural problem baked in 1970s era protocols that we have been using ever since. So let's come to the slide 3, the TCP tags. Now to understand why QIC matters, we need to understand what's broken about the current system, especially TCP. TCP or Transmission Control Protocol has been the backbone of the internet for decades, but it was designed in 1970s, long before smartphones, streaming or video calls existed. As it shows, there are three big problems with TCP, which we call TCP tags. The performance penalty we pay for using old technology. Problem 1, head of line blocking. Imagine like you are downloading 5 files at once. With TCP, if even one packet from one file gets lost, everything stops. All 5 downloads freeze and wait. TCP treats the whole connection as a single lane of traffic, so one accident blocks everyone. The second problem, handshake bloat. Before any data can flow, TCP has to do a handshake, a back and forth greeting between your device and the server. When you add security on top, TLC, that's 2 to 3 round trips before a single byte of real content reaches us. On a slow mobile connection, that delay is very noticeable. So the third problem is the rigid connections. TCP ties your connection to a specific IP address and port a so-called 4-tuple. The moment you switch networks, say like walking out of your house and your phone goes from Wi-Fi to 4G, your TCP connection dies. You have to reconnect from scratch. These aren't bugs. These are like the fundamental design limitations, and QIC fixes all three. Going forward with slide 4, the one-trip revolution. This is one of the most impressive things QIC does. It slashes the time it takes to establish a connection. While TCP plus TLC, you need 3 round trips before any real data flows. That means your device sends a message, wait for a reply, send another, waits again 3 times before your web page even starts loading. QIC collapses all of that into just one round trip by doing the transport handshake and the security handshake at the same time simultaneously. That's the combined handshake. But it gets even better. For returning user, people who have connected to a server before, QIC supports something called zero RTT resumption, 0 round trips. Your device already has cagged security keys from the last time, so it can send application data in the very first packet it transmits. Instant, like it is so instant, like no waiting at all. This dramatically accelerates what called TTFB, time to first byte. The moment your browser receives its first piece of content, the faster the TTFB, the faster the page feels. So, fluid mobility. Here's a scenario everyone has experienced. You're on video call at home on Wi-Fi, you grab your bag and walk out of the door. Your phone switches to 4G and suddenly the call drops or the app freezes or reconnects. That happened because TCP is rigidly tied to your IP address. QIC solves this with connection IDs. Instead of tracking your connection by IP address and ports, QIC assigns each connection a unique connection ID, a stable identifier that has nothing to do with your network address. So when you walk out of the house and switch from Wi-Fi to 4G, QIC simply migrates a connection to your new network. No drop, no reconnect, no loading spinner. Your streams just keep flowing seamlessly. This is what makes QIC a truly mobile first protocol built for how people actually use their internet daily. So, coming to the slide 6, solving congestion, let's go back to that traffic analogy because it's the best way to understand this. TCP is like a single lane highway. All your data, images, script, fonts travels in one line. If one car breaks down, every car behind it is stuck. That's head of line blocking and it baked into TCP's design. QIC takes a completely different approach. It is like a multi-lane highway. QIC sends data over multiple independent streams all within a single connection. Each stream is its own lane. So if stream A, say a large image, loses a packet and needs to wait, stream B, maybe your next maybe your page text keeps moving at full speed, completely unaffected. Each stream also has its own flow control window, meaning a slow or stalled asset can't drag down the performance of everything else on the page. The result? Faster, more resilient page load, especially on lose your congested network like mobile data. Now going to the next slide. So, hardened security. Security in QIC isn't an add-on. It's built into DNA of the protocol. Let's look at the three key security features. First is mandatory encryption. With TCP, you can run unencrypted traffic. Many older systems still do. QIC doesn't give you that option. TLS 1.3 is baked in from the very start. There is no plain text mode. Every QIC connection is encrypted always. Security isn't optional, it's foundational. So the second one is header protection. In TCP, even when the content is encrypted, a lot of metadata like packets, numbers and connection info is visible in the plain text. This let network middle boxes monitor and sometimes interfaces with traffic. QIC encrypt its own packet headers, reducing what observer can see and preventing a problem called protocol ossification, where middle boxes start depending on specific header formats and make it impossible to update the protocol later. Third, anti-amplification. QIC has built-in retry mechanism and strict address validation. This prevents attackers from using QIC servers as amplifiers in DDoS reflection attacks, a common abuse technique where small requests trigger a huge response sent to a victim. So, where does all of this leave us? QIC isn't just a technical curiosity, it's already running the internet you use every day. It powers roughly 70% of the Google's traffic, nearly 30% of the top websites globally already use QIC through HTTP 3. Companies like Google, Cloudflare, and Meta are already driving its adoption at massive scale. The bottom line, QIC isn't just the better alternative to TCP, it is the new foundation of modern internet, built for speed, built for mobility, and built for a world where being connected means never having to stop or reconnect. First, here in the Chrome, we will search for our website. Now this website is fully loaded. Now we will move to the Wireshark platform. Now we'll apply the filter QIC to display only the QIC packets over here. So here we can see all the QIC packets are here. So after applying the QIC filter, we can see different types of QIC packets. Initially we have observed like info, we can see there initial, then handshake, and then protected payloads, which are used to establish the connection. So here I have selected a QIC initial packet which is used during the connection establishment phase. So if we see over here, this packet uses a long header format which is used only during the setup phase of a QIC connection. Then the packet type is initial, making it the part of handshake process between the client and the server. Then if we see the version, this QoIC version 1, which is standardized version defined in RFC 9000. Then we can see the connection ID. The destination connection ID is used to identify connection, allowing QoIC to maintain the session even if the network changes. Here we can see. Then if we go inside the crypto frame, so this crypto frame carries the TLS 1.3 handshake data, specifically the client hello message. Unlike TCP, QoIC integrates security directly into the protocol. Then if we go to see this padding length, the padding is added to ensure a minimum packet size, which help prevent certain network attacks. Then if I scroll to, yes, protected payload. So after this handshake process is completed, QoIC switches from long header packets to short header packets for efficient data transfer. So when I have clicked on protected payload, so let me open this. Okay, so we can see this is a QoIC short header packet. It does not include fields like version or source connection ID, making it smaller and faster. These packets carry one RTT encrypted application data, which is used for actual web communication. So overall, QoIC uses long header for connection setup and short headers for efficient encrypted data transfer, which improves performance compared to traditional TCP.